All right, we're going to talk about algorithm efficiency here in terms of just how we can measure it. There's really two ways that we can look at efficiency. The first is basically size allocation or memory allocations. So how much storage space does our program take up? And then the second one is basically runtime. And both of those have their drawbacks in terms of reliability. Based on hardware components or processor speed. So we try to look at kind of an abstracted way to look at our efficiency. So what we're going to do is we're going to look at a couple of functions, and really what we're looking at is the amount of time it's going to take to run a function. So if we just declare a variable, we're going to say that just takes some constant time. There's going to be very little variation between how long it takes to just declare a variable. Same thing with setting, declaring, and initializing a variable. That would just be setting a variable, and then again we have another declaration and setting it. So we have all of these are going to take some set constant time, and if we add them all up, we're going to get a total constant time for this function. And so what we would say is, as a function of n, this, where n is going to be our size, this is just constant. It's not going to really ever take any different amount of time, which makes sense. There's no input. Everything is going to be just based on those constant values. And so we look at really order of magnitude differences between these types of functions. So if we look down at the function below, we can say this is the same constant time as before, but now what we do is we have a length. All right, and a loop, sorry, and it's based on an array up here that we're calling numbers, and this could grow, right? We could have a larger array. So like right now we have 6 values, but if we had 60 or 600 or 6 million, what would happen down here? And we can see this loop would take longer based on the size of the array. And so this is going to directly be proportional. It's going to be some constant time times the size of our array, so the length of our array. So as a function of n, this is going to grow linearly. As n goes to infinity, right, basically that's going to become this constant time here is going to drop out. It's going to become irrelevant, and really what's going to dominate this is this term here. And so what we say is this is an order of n. This is linear time, this is constant time. So this is called big O notation, talking about our order. So this is constant, this is linear. And we can see that this is going to grow as our input increases. Alright, so let's look at another couple of examples. As we look through this, we can see this one here is going to have some constant time, and now what we have is a loop within a loop. So for every iteration of this outer loop, we're going to go through this entire inner loop. And we just look and apply our constant times. That varies by n. This is another constant times n. And so what we're going to get is this is going to be an n squared value. So if we look at these, as we look at large values, what's going to dominate our function is this n squared term. And so this is going to be an order of n squared. We look at one more example. All right, this one is going to multiply by 2. So really what we're talking about is how many powers of 2 are going to go into this thing. And if we're looking for a power, what we're talking about is a logarithmic equation. And so this is going to be order of log n. And so we have all these different ways that things can look in terms of big O notation: constant time, linear time, squared time, logarithmic time. We could have cubic time. And if we start to graph them based on input and just look at their generalized curves, right, we're going to have time on our axis here and our input size, and as n grows, time is going to shift. This first one is going to be our constant time, or our big O of 1. This is going to be our linear time. This is going to be our exponential time, and then this is going to be our logarithmic time. And what we want to think about is if we're in this range over here, we're not going to see a lot of variation. It doesn't really matter what we pick. But as our input size grows, we're going to see that there's going to be a lot of difference in terms of our efficiency. And so when you hear companies or software developers talking about how things scale, as your input size grows, let's say you go from 10 users to 10 million users, you want to make sure that you are not on this exponential curve where now your processing speed is taking exponentially longer than a linear or logarithmic equation. You don't want to find that bottleneck as you're moving forward. So that's it, the idea of where we can do a purely kind of mathematical based evaluation of our code before we run it and before we find those bottlenecks.